Brake noise, arguably the most common of all customer complaints, is also one of the most troublesome to cure for both the brake engineer and the service technician alike. Many hours of intensive design and testing work goes into minimizing the amount of noise a system produces, even though noise has no effect on braking performance. In fact, a squealing brake is not an indication that the brake is working inefficiently. However, customer perceptions are different, and hence the large effort that is put into eliminating noise. The best cure for brake noise is to prevent it occurring in the first place. And the best way to do this is by correct servicing and installation, using genuine replacement parts. But before we examine these procedures, let us first look at the various types of noises encountered and some of their most common causes. Squeal and squeak would have to be the most common types of noises that the service technician has to deal with. These noises are caused by high-frequency vibrations when two or more components in the braking system reach the same natural frequency. When this occurs, we hear it as brake squeal or squeak. Whilst squeal and squeak are usually associated with disc brakes, drum brakes can also be prone to squealing, the only difference being in the components involved in producing the noise. These noises, or vibrations, can occur during braking from virtually any speed and at any stopping rate, and is the reason why a number of measures are incorporated in the original design and installation to minimize them. Groan or graunch is a noise that is usually encountered just as the vehicle is coming to rest from a low speed, and is caused by a momentary change in the lining material's frictional characteristics. The type of lining material used has a great bearing on whether or not this noise will be encountered, some materials being more susceptible than others. Weather conditions can also contribute to this problem. Vehicles which are parked outside, especially in wet or high humidity areas, may suffer from a condition known as morning sharpness. This condition is due to the lining material absorbing moisture during the cool-down period. This, in turn, causes the brakes to feel overly sensitive and prone to grabbing during the first few applications when the vehicle is driven after having been left standing for some time. Along with this sensitivity comes the groan and graunch. However, this is usually only a transient condition, which goes away once the lining material has reached its operating temperature. Judder is a wheel frequency vibration that is felt through the brake pedal, steering wheel, and body of the vehicle itself. The most common causes of judder in disc brakes is rotor thickness variation and rotor runout. Rotor thickness variation can also be generated by insufficient pad retraction or binding sliding calipers. This allows one pad to stay in contact with the rotor in the released position, causing the rotor to wear unevenly. Rotor runout, on the other hand, may be caused by uneven tightening of the rotor retaining bolts, or wheel studs being unevenly tightened and over-torqued by impact tools. It can also occur when the brakes are used repeatedly, with little cooling down time between applications. In these circumstances, temperatures are elevated considerably above normal, and should the casting of the rotor not be of uniform thickness all over, uneven cooling of the rotor will result. This uneven cooling causes the rotor to distort, which means it then has runout and eventually judder. Not surprisingly, ventilated rotors are more prone to developing runout than solid ones, there being more chance of casting thickness variations with the ventilated design. In drum brake systems, judder is usually caused by the drums wearing oval, possibly due to repeated heavy braking, or the handbrake being firmly applied when the brakes are extremely hot. Applying the handbrake causes that portion of the drum where the shoes contact to cool at a different rate, leading to distortion and judder. Yet another cause is hot spots in the drums. These are usually caused by a combination of heavy braking and lining materials which have high spots. These high spots cause uneven heat generation and rapid temperature rise, which in turn leads to hot spotting. The final noise we shall look at is hum. Hum is usually associated with rear disc calipers and only occurs at low speed, often when reversing. The usual cause is calipers that fail to release properly, leaving one or both pads partially applied. Over the years, vehicle manufacturers have continually striven to reduce the weight of motor vehicles as a means of increasing performance and economy. Since brake noise is greatly affected by component rigidity, the challenge for the brake engineer has been to reduce component weight without sacrificing strength or performance. Whilst these criteria may be at odds with each other, the challenge has been successfully met, with braking system performance increasing all the time. It has also meant careful attention to design detail and the addition of some brake hardware to reduce the noise levels which are always present in any braking system. Early fixed-head calipers used a step on the piston face as an anti-squeal mechanism, making correct alignment in accordance with manufacturers' recommendations of vital importance. This was then superseded by the use of steel shims between the pistons and pad backing plate as an additional means of dampening the high-frequency vibrations. These shims are usually marked in some way to facilitate correct assembly and may also require the use of some form of lubricant in order to increase their effectiveness. In some instances, the lining material itself is offset to the piston center line, making correct installation of the utmost importance. The early systems also used solid rotors, which are more prone to noise than the more modern ventilated designs. To help overcome this, a groove was turned in the outer edge of some discs to which was fitted either a welded ring or a wound-on wire. The idea behind this was to provide increased damping so that when the disc started to vibrate at its natural frequency, the energy would be used up in producing movement between the disc and the wire ring rather than in producing noise. Modern disc brake pads have anti-squeal material bonded to their backing plates, but may also employ an additional steel shim on the piston side pad. Others go further still, using special shim packs coated with lubricant and clipped to the pad backing plate. Finally, pad end flutter makes a significant contribution to brake noise, hence the use of clips which fit between the backing plate ends and caliper bracket on some systems. Removal or incorrect assembly of any of these shims or clips can lead to unacceptable high levels of noise. With drum brakes, we find that it is the shoe design that plays a major role in minimizing the amount of noise produced. A brake shoe must have a certain amount of flexibility, which will allow it to conform to the shape of the drum during braking. Making the shoe flex ensures even contact over the whole shoe and not only reduces noise, but also increases braking force. To achieve this, brake engineers spend many hours in design and testing to arrive at the correct profile of the shoe web. In some cases, specially shaped slots are even cut into the web itself to achieve the correct degree of flexibility. Also of significance in the reduction of noise is the way the shoes are located against the backing plate. Brake shoes are commonly held firmly against their backing plates by some form of spring or clip and anchored at their ends by wheel cylinders or anchor points. It's worth noting here that even with these clips and anchors to reduce shoe vibrations, most manufacturers recommend that some form of high-viscosity lubricant, such as caliper slide grease, be applied to the shoe ends and where they contact the backing plate. Having now looked at the various types of brake noise and some of the design variation used to minimize them, we shall now go through the correct procedure for fitting a set of new disc pads and brake shoes. Because the new pads will be thicker than the old worn ones, the pistons and the calipers will have to be pushed back into their bores to allow the calipers to be refitted. This will displace fluid back into the master cylinder reservoir. To prevent it from overflowing, The fluid level in the reservoir should be first lowered by approximately 2/3 of its capacity. The vehicle can then be raised and the wheels removed. Once this has been done, the first step in any reline process is an examination of the brake system components. We shall start with the disc rotor. Rotors should be checked for runout using a dial indicator and thickness variation, preferably using a micrometer for accuracy. In the absence of these, a reasonably accurate check can be made by rotating the disc by hand with the caliper and pads still in place. If the rotor drags appreciably in one place as it rotates, it can be assumed that some amount of runout or thickness variation exists. In addition to this, a smooth rotor surface is essential for correct bedding in of new lining material and the prevention of noise. It should be noted, however, that smooth does not mean glazed. A highly polished surface that readily reflects light will not allow modern lining materials to bed in correctly, and is especially true for semi-metallic linings. Should any of these conditions exist, the rotor, providing it is not below its minimum thickness, will require machining. Rotors which have been machined to or past their maximum limit will have to be replaced. A point worth mentioning here is that after the caliper is removed, it should be suspended from a piece of wire attached to some part of the suspension or body. This prevents the dangerous situation of the brake hose having to take the weight of the caliper. Rotors should always be machined in 2 stages. The first stage is used to remove all surface irregularities and is done in even cuts from both sides of the rotor to a depth of between 0.125 and 0.25 of a millimeter. Tool feed speed should be 0.15 to 0.25 of a millimeter per revolution. The final cut is done to a depth of approximately 0.1 of a millimeter on both sides of the rotor, tool feed speed being 0.05 of a millimeter per revolution. This slow speed is necessary to give an acceptable surface finish to the rotor. To finish off, 120 grit emery paper is used to remove any traces of graphite brought to the surface by the machining process, which could contaminate the surface of a new pad. Also, by moving the emery with a circular motion, a non-directional swirl pattern, necessary for today's semi-metallic and non-asbestos lining materials, can be achieved. The last important point about disc rotor machining that is often overlooked is the final disc thickness. Disc rotors should be the same thickness on both wheels of an axle. This ensures that both rotors heat up to the same rate, maintaining stable braking performance as the temperatures rise. And remember, whether the disc has been removed for machining or not, the wheel bearings must be adjusted in accordance with manufacturer's recommendations. We can now turn our attention to the brake calipers. If they are the type where the brake pads are held into them by clips, the pads should also be removed at this point. Following this, the pistons should be pushed back into their bores. The pistons must slide easily into their bores, and should any difficulty be experienced, both calipers must be overhauled to ensure that the pistons will retract properly. Once the pistons are pushed back, the caliper assemblies can then be checked for serviceability. The first points to check are the slides. You should be able to move them their full distance using only light finger pressure. Slides that are tight or seized prevent the pads from being pulled completely away from the disc. This leads to the pad overheating, excessive disc wear and thickness variation problems, brake fade, fluid vaporization, and increased fuel consumption. Due to the importance of the slides being able to move freely, PBR recommends that they be removed completely, cleaned and relubricated using special caliper slide grease each time the brake pads are replaced. Also, if any of the rubber boots which prevent water and dust entry are torn or damaged, they should be replaced at this point. Following this, the piston dust boot should be inspected for tears and brittleness. Torn boots or brittle ones that are likely to tear soon allow water and dirt to enter. This in turn allows corrosion to form between the piston and the caliper body, requiring higher pressure to move it and preventing it from retracting properly. As the corrosion continues to build, it gets to a point where the piston finally seizes completely and the brake no longer works. If any of these problems are present, both calipers from the axle should be overhauled. Once the inspection or overhaul has been completed, the new pads can now be fitted. Care should of course be exercised in ensuring all noise suppression shims and clips are reinstalled. Whilst some manufacturers place the shims on the back of the pads dry, others recommend that 80% of the shim surfaces be coated with caliper grease, as shown here. Another common recommendation by some manufacturers is the use of caliper cement. This is usually employed in systems that do not use shims and is shown here being applied to a set of pads prior to fitment. All these methods are aimed at increasing the amount of damping in the system, and because of the number of different methods employed, manufacturers' procedures should always be followed. In addition to this, the places where the pads rest in the caliper support should be coated with a small amount of caliper slide grease to also help dampen pad vibrations. The caliper can now be replaced, making sure that any anti-rattle springs or clips are positioned correctly on those systems that have them fitted. Caliper and anchor mounting bolts should always have their threads cleaned and a small amount of thread locking compound applied to them before being replaced and torqued to manufacturer's specifications. In some cases, manufacturers require that these bolts be replaced each time they are removed. In this case, new bolts are included with genuine replacement pads and their threads already coated with a locking compound. The wheels can now be replaced and should be tightened evenly in an alternate pattern to the manufacturer's recommended torque. This ensures that the disc rotor will not be distorted, causing disc runout and judder. Once the wheels are replaced, the brake pedal should be slowly pumped approximately halfway to bring the pads into contact with the disc rotors. We've now reached the point where we can road test the vehicle and bed the pads in, but before we do, the master cylinder should be topped up with the correct grade of brake fluid. PBR does, however, recommend that when replacing brake linings, the fluid should also be replaced. Bedding pads, or burnishing them to give the process its correct name, is done to bring the resins in the pad to the surface, giving it the correct frictional properties and preventing premature wear. The golden rules when bedding in pads are don't get them excessively hot and don't drive with your foot resting on the pedal. The correct procedure is to accelerate the vehicle to 60 kilometers per hour and then, using moderate pressure, slow it to 10 kilometers per hour. The vehicle is then accelerated again back to 60 kilometers per hour and the process repeated 10 to 15 times, leaving a half a kilometer between brake applications to allow temperatures to stabilize. Now, here's a few tips on the process. Firstly, unburnished pads take longer to slow or bring a vehicle to rest, so don't tailgate other vehicles. Secondly, try not to stop the vehicle during the process, as this may put excessive heat into the pads. Thirdly, when finished, let the car stand for some time to cool the pads before returning it to the customer. This will prevent them from overheating and damaging the pads. And finally, a word on brake pads. Brake engineers spend many hours of testing to arrive at a compound that will suit the vehicle under a variety of driving conditions. Take advantage of all their hard work and use the pads that are recommended by the manufacturer. Having covered disc brakes, we will now turn our attention to drum brake relining. As with the disc brake rotor, drum surface condition is of the utmost importance when it comes to bedding in a new lining material. Surface smoothness, runout and glazing being just as important for correct drum brake operation as it is for the disc brake. This means that in the majority of cases, the drums will need machining each time the brakes are relined. As the machining procedures are basically the same for drums as discs, we will not go over them again except to stress the importance of two main points. The first is that drums have a maximum diameter that they can be machined to, and the figure is usually cast into the drum. Drums need to be checked for size before and after machining. They should also be the same diameter on both wheels of an axle, and if oversized, replaced in pairs. The second is that cleaning the freshly machined surface with 120 grit emery after the final cut has been made is vital to remove any of the graphite which may have come to the surface during the machining process. The new brake shoes should be ground to the radius of the drums. This highlights another reason for ensuring that the drums on the axle are the same diameter, because it allows all the shoes to be ground to the one radius, eliminating the risk of mix-up during assembly. As this video is primarily interested in the subject of noise minimization, we will not be addressing the hydraulic side of brake relining. We would, however, like to stress that any brake reline should be accompanied with either the replacement or overhaul of all wheel cylinders on the axle being relined. Following the machining of the drums and shoes, the backing plate should be thoroughly cleaned and the shoe support nibs lubricated with caliper slide grease. It must be stressed that this is only a light coating. Too thick a coating could melt and contaminate the lining material under high temperature conditions. Before commencing assembly, handbrake and shoe adjusting mechanisms should be cleaned, but not lubricated. The reason for this is that the lubricant tends to trap the road grime and brake dust, which in turn seizes the adjuster, preventing it from operating. The adjusters can then be backed completely off prior to assembly. This will ensure that correct handbrake and brake shoe geometry is maintained when the shoes are adjusted after the reline is completed. Brake shoe retraction springs and hold-down clips should be examined for signs of stretching, nicking, or distortion. Should any of these be present, the springs or clips should be replaced in sets for both wheels on the axle. The brakes can now be reassembled with a small amount of caliper slide grease applied to the shoe ends. Once assembly has been completed, the brake shoes and handbrake can then be adjusted. When adjusting drum brakes, the handbrake should always be backed off and the shoes adjusted first. This ensures that when the handbrake is adjusted, the apply lever is back against its stop in the released position. Then, when the handbrake is applied, the maximum amount of force is applied to the shoes by having the angle formed between the lever and cable as close to 90 degrees as possible. On systems with adjusting apertures, the shoes should be adjusted until the wheel locks solid and then backed off until a light rub can be heard when the wheel is spun by hand. This, of course, means that any self-adjusting mechanism will have to be held away from the adjuster whilst being backed off. A piece of welding wire can be bent to do this, and a useful tip is to bend up the wire and leave it in place before putting the drum back on. If, on the other hand, no provision is made in the backing plate for adjustment, the shoes will have to be adjusted so that whilst the drum can still be easily replaced, a light rubbing noise is heard when it is rotated. Failure to do this may mean that the brake will never adjust owing to the fact that the master cylinder may not displace enough fluid for the self-adjusters to work. Or, in the case of an old master cylinder, the cylinder bore may be damaged by dirt picked up when it travels further than it normally does. Our last adjustment is the handbrake, and once correctly adjusted, should not need adjusting again until the next reline. Whilst this may sound an unusual statement, remember that the clearance between the shoes and the drum is controlled by the shoe adjuster and not the handbrake lever. The simplest way to adjust a handbrake is done with the wheel on, but clear of the ground. The handbrake is first applied 2 clicks on its ratchet, and the cable is then adjusted until a slight increase in the effort to turn the wheels is felt. The adjuster can now be locked up, and the adjustment is complete. All that is required now is the road test and initial bedding in procedure. The same procedure that was used for disc brakes can be used for drums. And remember, don't get them too hot, or the lining material will be damaged. Now, one final word about the relining process. New linings are more compressible than properly bedded-in linings. This means that initially the brake pedal may feel slightly spongy for the first week or so of operation. This is perfectly normal, and the pedal should return to normal after that. So remember to tell your customers to prevent any misunderstandings. Also, whilst we have shown the fitting of new linings, the procedures shown can also be applied to linings that are already in service, but not near minimum thickness. By following the procedures covered in this video, brake noise in both drum and disc brakes can be kept to a minimum. However, before we end, let's just recap on what we've learnt. Brake noise, whilst annoying, is not a sign that the brake is working inefficiently. Brakes can produce a variety of noises caused by different components in the system. Squeal or squeak is usually caused by two or more components in the system vibrating at the same natural frequency and can occur at virtually any vehicle speed. Groan or graunch, on the other hand, usually occurs just as the vehicle comes to rest from low speed. This is usually attributed to the lining material being particularly true when the material is cold, such as first thing in the morning. Judder is a low-frequency vibration that is felt through the brake pedal and steering wheel. In disc brakes, this is usually caused by rotor runout or thickness variation, whilst in drums, ovality and hot spots are the main offenders. Our final noise was hum, which occurred at low speeds and was usually associated with disc calipers which failed to release properly. It was then pointed out that the weight and size of vehicles, along with their braking systems, had been steadily reduced in the search for greater fuel economy, and that this had resulted in additional design features and hardware having been incorporated to minimize brake noise. One early method was the introduction of a stepped caliper piston to control the force distribution on the pad, later being supplemented with the addition of vibration dampening shims and the offsetting of lining materials to the piston centerline. The early solid disc rotors themselves also had a vibration dampening steel ring fitted to a groove on their outside edge. Whilst in modern systems with ventilated rotors, the pads have anti-squeal material bonded to the backing plates, shim packs, and clips between the backing plate ends and caliper bracket. With drum brakes, however, we found that it was the design of the shoe that played the most significant role in noise reduction. Brake shoes were specially shaped and, in some cases, slotted to allow the shoe to flex and contact the drum correctly, whilst at the same time being held firmly against the backing plate. It had earlier been said that correct assembly methods greatly contributed to noise suppression, and we started by looking at a disc brake. First, we checked the disc rotors for runout using a dial indicator, and then thickness variation using a micrometer. We also showed a quick checking method where the disc is rotated by hand. A disc rotor with either of the previous problems would tend to drag in one position as it was rotated. It was also noted that a smooth, unglazed rotor finish was vitally important to provide the correct surface finish for new pads to bed in on. This highlighted the fact that most rotors would require machining, or if undersized, replacing during a brake reline. We then turned our attention to the calipers themselves, first checking that the pistons would slide back easily into their bores, followed by free movement of the slides on floating caliper designs. Due to the importance of the slides in correct brake operation, it was recommended that they be removed from the caliper mount, cleaned, and re-lubricated using caliper slide grease each time the pads are replaced. Finally, the calipers and slides were inspected for torn dust boots and slide seals. We then turned our attention to the pads themselves, stressing that all noise suppression shims and clips should be reinstalled. In addition to this, it was pointed out that some manufacturers recommend the use of grease, such as caliper slide grease, be applied to at least 80% of all shim surfaces, whilst others use disc cement, highlighting the importance of consulting the relevant servicing information. Caliper grease was also applied to the caliper support where the ends of the pad sit. And as the caliper was replaced, any anti-rattle springs or clips were checked for correct positioning. It was also noted that some manufacturers recommended caliper mounting bolts be replaced with new ones, pre-coated with a thread locking compound, whilst others require that the threads on the old bolts be cleaned and the locking compound applied to their threads. The final step in assembly was to replace the road wheels and tighten them to the correct torque in even stages, using an alternative pattern to prevent disc rotor distortion. We then looked at a pad bedding in procedure, but noted that before moving the vehicle out of the workshop, the brake pedal should be slowly pumped about halfway to bring the pads in contact with the disc rotor. Bedding in was then accomplished by driving the vehicle at 60 kilometers per hour and then using moderate pedal pressure to reduce the vehicle speed to 10 kilometers per hour. This process was repeated 10 to 15 times, allowing approximately half a kilometer between brake applications to allow the pad temperatures to stabilize. Excessive heat being the big enemy of new brake lining material. The final step in the bedding in process was to allow the vehicle to stand for some time before returning it to the customer. With drum brakes, run-out and surface condition were found to be just as important as with disc brakes, and that whether the drums are machined or not, they should be the same diameter on both wheels of an axle. Also, irrespective of whether the drums were machined or not, the shoes should be radius ground to suit drum diameter. We followed this with a reminder that the hydraulic cylinders should always be overhauled or replaced whenever the brakes are relined, and that the backing plate be thoroughly cleaned and a small amount of caliper slide grease be applied to the shoe support nibs. After that, the brake shoe and handbrake adjusting mechanisms were cleaned and backed off completely, followed by a visual inspection of the shoe retraction springs and hold-down clips. The shoes were then replaced using a small amount of caliper slide grease on their ends. The final step before bedding in was the adjustment of the brakes and handbrake, and it was pointed out that on systems that had apertures in the backing plates, the brakes should be locked completely before being backed off to the point where a light rub was audible when the wheel was rotated by hand. It was also noted that on systems where self-adjusters were fitted, a small tool would have to be bent up out of wire to hold the adjusting lever away from the adjusting wheel when the brakes were backed off. On systems where an aperture was not provided, the shoes would have to be adjusted until they lightly rubbed against the drum when it was rotated. The handbrake was then adjusted by applying it 2 clicks, moving the adjustment until a slight increase in resistance could be felt when the wheels were rotated, and then locking up the adjustment. Bedding in procedures were said to be basically the same for drum brakes as they were for discs, and we stressed the fact that it would take 1 or 2 weeks for the brake pedal to become completely firm, owing to the greater compressibility of new lining material. PBR Automotive Proprietary Limited hope this video has been of assistance in helping you minimize customer brake noise concerns. For other braking problems, we refer to the other diagnostic videos in the series.